Okay, so good morning, everybody. Happy New Year to everybody. May you all have 10 pointers in this year. And may you all get extra credit in every exam problem. Okay. Oh, not December, man. 2021. Okay, fine. I'll talk about spherical harmonics, and then once we're done with that, then I will cover addition of angular momentum. At least 2 classes on that I want to hold, and we have sufficient number of classes in the coming week, and after that, so I can quickly see how many classes are left. Let's see. Today is first, so we have. 5, 6, 7, 8, and 12, 13, 14. Okay, so and then but 6 we are going to have our quiz next week. So 5, 6, 7, 8, 12, 13, 14, that is 7 classes. But I don't want to hold 7 classes. Obviously, I don't think you want to go. So I'll try to finish by January 8th. Okay, so today I'll talk about spherical harmonics. Then January 6th, 7th, January 6th, 7th, and 8th, I'll talk about whatever topics are in there. Okay. Okay, and so let's start with this. So one good reference for reading about spherical harmonics is this thing. Well, any undergraduate quantum mechanics textbook, such as well, Zetley is like a sort of a mixture between undergraduate and graduate. But otherwise, any Griffiths, and then I can't really think off the top of my head what else is good undergraduate. Then books on mathematical methods. So if you mathematical methods. So a typical example of this is Arkin and Weber. Another very nice reference is one book by Mary L. Boas. It's not very common in India, but it's a very nice reference. Very beautiful reference. Yeah, so this is this, and then of course you can go online and you can find a full ocean, a vast ocean of references, right? Okay. All right. So what are spherical harmonics? As we have discussed already, they are eigenstates of the angular momentum operator. All right. And what is the angular momentum operator? That also we have So let me actually 1 second. Arcane. Do you all have a copy of Arcane?
Yes, sir. Soft copy.
Yes, sir.
Yeah, of course, everything is soft only these days. So he has a whole chapter on this, chapter 11, Legendre polynomials and spherical harmonics. Okay. Sorry, I wasn't planning on teaching spherical harmonics, so like I just have to go and look a little bit. So this, by the way, Arcane has a lot of information, okay, and maybe all that information is not new. You know, it's good if you study all of that, but it's not like so essential. Okay, so I'll work with Zeki instead. Okay. So spherical harmonics are solutions of Laplace's equation. Or I should say, well, they are eigenstates of the Laplacian. Eigenstates of the angular Laplacian. Okay. Now we have looked at one component of the spherical harmonics, right, which is the eigenstate of the Z operator of the Z angular momentum. So let me go over that in. So this is y dx. Okay. So now if you switch to either polar coordinates or spherical coordinates, either way it doesn't matter. This Lz becomes IH bar d phi. So are you all comfortable with me just leaving this here, and is it something that you can work out on your own?
Yes, sir, we can do this.
Yeah, ठीक है ना? This is like this. You have to. Yes. Shubham, you were saying something?
Yes.
Is it okay? मतलब this is just algebraic manipulation, ठीक है? Okay. I can't really. The voice is not clear. I'm sorry. Okay. So then we have the other two terms, right? Lx and Ly. So okay. So let's see. So what is actually another way to get this slightly faster way? So R cross P, which can be written as minus IH bar R cross the gradient. So you can also alternatively just work with the gradient operator in spherical coordinates. So the gradient operator, you know, in Cartesian coordinates can be written like this: x dx, y dy plus z dy. Right? So you can translate this into spherical coordinates by again, using the relationships, x is equal to r sine theta cosine phi, y is equal to r sine theta sine phi, and z is equal to r cosine theta, right? And the inverse relationship is r is equal to root of x square plus y square plus z square. Theta is equal to what is it? Tan inverse of root of x square plus y square divided by z, and phi is equal to tan inverse of y by x. Right. So these are your spherical coordinates. Okay. Now another important so now in terms of the spherical coordinates, one can write this gradient operator, right? So I'll show you one component. So dx, dou by dx. Now x is a function of three variables, right? So if I want to write dou by dou x in terms of dou by dou r, dou by dou theta, and so on, what do? I use the chain rule, right? So I write dr by dx, d by dr, d theta by dx, d by d theta, d phi by dx, d by d, like this, right? So you can do the same thing for y and z. So dr by dx, for instance, you can look at this expression, and when you take the derivative, you'll get x by r. Similarly, you can work out what this thing is, and it will come out to be something like 1 by sine theta, I think, and something similar for the phi component. Okay, or there'll be some factor of cotangent or something. Right? You'll have to look into that. And then what about the unit vectors? The unit vectors can also be expressed accordingly. All right. So what is x hat in terms of r hat and theta hat? So you have the three unit vectors. You have r hat. You will have phi hat, and then you will have theta hat, which is perpendicular to the both of these. So I'm just drawing the two-dimensional projection of the three-dimensional plane. Okay. So you can write down x in terms of, so first it's easier to write down the unit vector for r. So r is equal to the vector r divided by the magnitude of r, right? And what is the vector r? The vector r is in terms of x and y. This has the coordinates x, y, or since we are in three dimensions, x, y, z divided by r, right? So you can write this as x by r, y by r, z by r. So in terms of the x hat, y hat, and z hat components, r hat can be written as, so x by r becomes this sine theta cosine phi. So you can write it as sine theta cosine phi times x hat, right? This is the x hat component, plus sine theta sine phi y hat plus cosine theta z hat, right? So you get one set of relations between the unit vectors and another set of relationships between the derivatives. So similarly, you can write theta hat as something times x hat, something times y hat, something times z hat, like this, right? and same thing for phi hat. Then you can invert these relationships. You can invert these relationships to write x hat as a function of r hat, theta hat, and phi hat, and likewise for okay. So these are some functions f, g, h of these unit vectors. So what you do now is you substitute these expressions in here in x hat, y hat, and z hat, and likewise you substitute the expressions for the partial derivatives here for dou x, dou y, and dou z. So it's a long and tedious calculation, but everybody has to do this calculation in their lifetime. So can you all do this on your own?
Yes, sir.
Okay. So this is very important. I mean, there's really no substitute. You have to do it on your own, unfortunately. Right? This is just one of those things. Okay. So when you work out this, what this gradient operator looks like, this gradient operator in spherical coordinates, what you find is that it can be written in this way: r hat dou r plus theta hat pi r dou theta plus phi hat by r sine theta dou phi. Okay. And right. And if you compare it to the expression for the gradient operator in Cartesian coordinates, you can see that there are some similarities, right? For instance, right, it looks like either one of these terms, right? But what about the theta hat term? So the theta hat term has this same kind of structure, theta hat times d hat, dou theta, right? But in order for the dimensions to work out, right? What are the dimensions? So the unit vectors are dimensionless. And what is the dimension of the gradient? Dimension of gradient is L inverse, right? And the dimensions of the unit vectors are 1, right? For any unit vector. And dimension of the derivative is L minus 1. Dimension of the angles is, they are dimensionless, right? So the derivatives with respect to the angles are also dimensionless. So this term has dimension L inverse, right? So in order for this term to have dimension L inverse, you have to put a R 1 by R factor here. Same thing for the phi d phi term, but in addition, you have to put a sine theta term, right? Why is this sine theta term needed? Because if you look at spherical harmonics, right? As you go up and down, right? What are you doing? You're taking this this theta angle. This theta is your azimuthal angle, and as you change it, right? What happens is that the size of the circle changes, right? And how much does the size of the circle change by? This is r, right? This is the radius vector. This angle is theta, and what is this? What is this radius? This radius is r sine theta. So you have to divide by an angle, but which angle should it be? You have to divide by a radius, but which radius should it be? Should it be this radius or this radius? It has to be the radius at the correct angle. So it's r sine theta. Okay, but once you go through this very long and and tedious calculation, you will get the same result. All right. So once we have this expression, we can quickly write down the angular momentum. The angular momentum now is R cross P, and P is, so this becomes minus I by H bar R cross the gradient operator, right? That is the definition of the momentum. So this becomes minus I by H bar R cross with this expression. So this expression, let me write it like this: dr 1 by r d theta 1 by r sine theta dou phi, right? So this is the r hat component, this is the theta hat component, and this is the phi hat component, right? Now what is the vector r? I can write the vector r is the magnitude times the unit vector r, right? So when I take this cross product, I have to take the cross product of r hat with r hat. What is this going to be? Cross product of r hat with r hat, 0, right? Any vector cross product with itself is 0. Then I have r cross r hat cross theta hat, right? And what is this? This is going to be phi hat. And then I will have r hat cross phi hat, and this will be minus theta hat, right? Because r, theta, and phi, these three form a orthogonal set of vectors, right? So if you look at this this spherical coordinate picture, r hat is pointing outside, right? Theta hat is pointing down, right? This is theta hat, and phi hat is pointing in the direction tangent to that circle. So something like this, right? And it forms a right-handed basis. So it has the same sort of properties that x hat, y hat, and z hat do, right? So when you put in this relationship here, you get r hat is equal to I h bar r okay, 0. R hat cross r hat is 0. R hat cross theta is phi hat. So you get so the theta component Shubham, can you please mute yourself? I can't mute you for some reason. Pata nahi, I don't know what the problem is. Shubham?
Sorry, sir.
Mute kar lijiye, please. You are not muted. I don't know why you are not muted, and I don't know why I can't mute you. पता नहीं, हो सकता है आपने Zoom हैक कर लिया है. Who knows? So R, ठीक है, वो rejoin कर लेगा. R cross theta will give you the phi component, and the magnitude will be this 1 by r sine theta. So you will get 1 by r d theta, and the theta component will give you r cross phi minus, you will get minus 1 by r sine theta d phi. Let me just check my expression. कुछ गड़बड़ है मेरे expression. Gradient operator is हाँ नहीं सही है, सही है, right. So this is the angular momentum operator, and if you multiply out the factors of r, r will cancel out, and finally you can write this as minus IH bar phi hat dou theta, which is this component, minus theta hat by sine theta dou phi. So this is your angular momentum operator in spherical coordinates. Okay. So I hope the steps in this procedure are clear. If they are not, you please let me know. But like I said, you have to sit down and work through all of this yourself. Just watching me do it is not going to, help you in any way. Now one can ask, what is Lx? What is so if I write L, right? I know that it can be written in these components Lx, Ly, and Lz. I know what the expression for this Lx, Ly, and Lz is in my Cartesian coordinates, but I can also get the expression by taking the dot product of this L vector with x hat. Right? This is the definition of the x component of any vector, right? It's the dot product with the unit vector in that direction. So I can take this guy and take the dot product with x hat, and x hat, as I told you, you can derive what x hat is. Let me write down the expression for you. X hat looks like this: sine theta cosine phi r hat plus cosine theta cosine phi theta hat. So all of these expressions, by the way, I am also looking at exactly as I'm writing them down. Okay, it's not as if I remember these by heart. So you can take this x hat and dot it with L. If you take this and dot it with L, what will happen? R with phi and R with dotted with theta will go to 0, and you can write down Lx. The only non-zero component will give you you will get from theta and phi, right? And so Lx can be written down as this times sine phi d theta plus cotangent theta cosine phi d phi, right? And this is the same as writing it in terms of Cartesian coordinates, which would be y dou z minus z dou y. These are equivalent ways of writing this operator. Okay, so yeah, it's okay, Aman. I mean, if you have network problems, as long as you watch it online, and if you have questions, please ask. So it turns out that there are some people who are spamming the YouTube live chat. Somebody is saying India no good, something. Like, you don't have anything better to do than to go on somebody's YouTube live chat quantum mechanics class and say that. Silly. Okay, so now let's finally come to the crux of the issue, which is that these are eigenstates of the Laplacian. Now, what is the Laplacian? The Laplacian is this del square operator. Okay, right? And it's the most important, you can think of it as the most important operator in physics. In everywhere you go, Laplace's equation, Helmholtz equation, wave equation, Schrodinger equation, everywhere this shows up, right? So in Coulomb's law, right, in electromagnetism, everywhere this equation shows up. So when I say what are eigenstates of the Laplacian, what do I mean? I mean that eigenstate of any operator, right, means that this is equal to, this is the eigenvalue equation, right? It means that I have some operator which acts on some function, and the answer is the same function multiplied by the eigenvalue. This is the, okay. Now, so what is this del square? If I look in Cartesian coordinates, del square is just this operator, dou x squared, dou y squared, dou z squared, right? And if I ask what are the eigenvalues of this operator in Cartesian coordinates, again I can work that out relatively easily. Let me just ask first of all, what are the eigenvalues of dx square? So that means what function satisfies this relationship, right? That dx square f is equal to lambda f. What is the answer? Anybody? What is f of exponential, right? It's going to be exponential of lambda x. Sorry, with a minus sign. Or it can also be exponential, right? So better to work in terms of, write it like this, plus minus I lambda, right? So this lambda, we should normally label it with kx instead of, right? So what are the eigenstates? Exponent e to the plus minus I kx times. Same way for this, what do you call it? So this lambda becomes, right, so this should not be lambda, this should be root lambda. Same way for dou y square, I can write this as minus ky square g, and dou z square h is equal to minus kz square h. Now, in general, what happens is the eigenvalues are negative. That's why we are writing ky square kz square. But you can also have complex eigenvalues. You can have imaginary eigenvalues, in which case, or positive eigenvalues, in which case kg, this ky, kx, and kz, these would just become imaginary numbers, right? So that you get a positive sign. So I can now write down what the general Laplace, what the general solution of this equation is. And the answer is exponent, right? So I'll write it like this, minus k square psi minus plus minus I vector k dotted with vector r. What is k? K is some vector kx, ky, and kz. And what is this k over here in the eigenvalue? This k is the magnitude of the vector k. And r is just the pointer, okay? And what are these? These are plane waves. Right? So is this fine? Okay. If there are any issues, you please ask me, okay? I keep checking on the Zoom chat and on the YouTube chat for any questions, but you can also just ask at any point. So this is the solution of the eigenvalue equation. Now, once again, you don't need to have necessarily negative eigenvalues. You can have positive eigenvalues, in which case these components will become complex. Okay, so this is the same thing that we had, if you remember, in whenever you solve the Schrodinger equation, right? This thing comes up. Now, what about the Laplacian in spherical coordinates? So the same thing, this Laplacian. So what is this operator? We can write it as the del dot del, right? Gradient dotted with itself. So what is the expression of this operator in spherical coordinates? Well, I can take the expression for L, which we have worked out. This is the expression for L in spherical coordinates. Sorry, not 1 second. We want this gradient. So the gradient in spherical coordinates, where is the gradient? Yeah. Where is it? Gradient in spherical coordinates. Yeah, this expression. So this is the gradient in spherical coordinates. And we can use this expression. Okay, this is the gradient. So I can write down the dot product of this guy with itself. And again, using the fact that r dot theta and r dot phi, r hat dot phi hat and so on are 0, what will you get? You will get dr square, right? Plus 1 by r dou theta, 1 by r dou theta. This is important, okay? Because, so let me write it as, let me work it out explicitly so that you can see what is going on. R hat dou r plus theta by r dou theta plus phi hat by r sin theta dou phi. Okay, so you're taking the dot product of this operator with itself. When you do that, what will happen? R hat and r hat will give you 1 and you'll get dou r. Theta hat and theta hat will give you 1. And now you see this is dou theta by r acting on dou theta by r. So you'll get 1 r by r dou theta acting on 1 by r dou theta. Same thing for the phi hat term, okay? So you get 1 by r sin theta dou phi acting on 1 by r sin theta dou phi, like this. Okay? Now, in this case, there is nothing special because r is independent of theta, right? R, theta, and phi are independent coordinates. So this term just becomes 1 by r square dou theta square. 1 by r will just come out. And same thing here also, r sin theta is independent of phi, so you will get 1 by r square sin square theta dou phi square. Okay. So this is your Laplacian in spherical coordinates, and this is an expression which you should remember. Okay, this is not an expression which you should need to look up. You should remember this. And Laplacian in spherical coordinates. Now, what if you're in 2 dimensions and working in polar coordinates? In polar coordinates, what will happen? The phi term will just go away and your Laplacian will just be this, right? And what if you are in cylindrical coordinates? In cylindrical coordinates, well, cylindrical coordinates are a combination of polar coordinates combined with the z-axis. So what is your Laplacian there? It is this for the polar part, r theta part, and this will just become dou z square. Okay, because then z will just be a Cartesian, ordinary Cartesian coordinate. So this is your Laplacian. Okay. Now we can compare this. Okay, so now if you remember, we have this expression for the angular momentum operator L. Okay. Now we should also look at what is L square, right? The L square operator is going to be L dot L, and I don't think I worked that out. No, I didn't work that out. So if I take the dot product of this guy with itself, what do I get? I get L square minus h bar squared, right? Once again, taking the dot product of these terms with themselves, phi dot phi will give me dou theta squared. Theta dot theta will give me, the minus sign will go away. I'll get 1 by r square sine theta dou phi square. Okay. But now if you look at this expression for the Laplacian here, and you look at this L square term, you can see that basically this angular part of the Laplacian is the same as the L square term. Right? So now the Laplacian in spherical coordinates can be written like this: dou r square plus 1 by r square dou theta square plus 1 by r square sine square theta dou phi square. You can see that these two are identical, right? So this, right? These two are identical. So I can write this as dou r square minus L square by r square h bar square. This is the Laplacian in spherical coordinates. So there is a component which depends on r, and the remaining component is a function of L only. And we can, if you look back at the previous lecture notes, this is the same expression that I had given you in one of the other classes. Right. So this is the Laplacian. I had given you something which involved this 1 by r square. Let me check it. Yeah, one second. Yeah, so I'm one mistake I made somewhere, right? When I derived this del square, I got something wrong here. What did I make? I made some mistake. I made some mistake. What mistake? Tell me. Yeah, somebody is trying to tell me something.
Sir, study class you miss minus h square in
Where?
L
Sorry?
square term. Study class L square in L square term, sir.
In L square term, in what, this term? What did I miss?
सर स्टैटिक सर आपने जो कल एल स्क्वायर का डेरिवेशन किया था उसमें एच कट स्क्वायर आता है, लेकिन आपने उसको कट कर दिया था एच कट स्क्वायर।
हाँ राइट 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 राइट, वो कर दिया था मैंने, राइट। अब वापस आ गया। सॉरी, बहुत ज़्यादा डेरिवेशंस हो रहे हैं, तो वो मैंने क्यों कट कर दिया था। एक सेकंड, एक बार जाके फिर से देखिए। नहीं, तो इसको नहीं नहीं कट करना चाहिए था, मेरी गलती थी। ठीक है, नहीं कट करना चाहिए था इसको, तो इसको रखिए, ये जरूरी है। और बताइए, और कुछ। अब ये डेल स्क्वायर में मैंने क्या गलती करी? डेल स्क्वायर में हम मेकिंग
डेल स्क्वायर में 1/r स्क्वायर डेल बाय डेल आर इंटू आर
हाँ
डेल बाय डेल आर होता है टर्म।
हाँ, आई नो, बट व्हाई इज दैट? why is that coming? Because if I just take the gradient operator, एक second, the gradient operator क्या है? Okay. हाँ, ओके, मैं थोड़ा जल्दबाजी में कर रहा था काम, तो ये डॉट प्रोडक्ट में थोड़ा सा यू हैव टू बी लिटिल बिट मोर केयरफुल, बिकॉज you can't just, why, for the same reason you can't just say theta, क्या कहते हैं, you can't just say that r dot theta is 0, क्योंकि the expression is not r, it's actually dou by dou r of theta will also come into that picture. Okay, so anyways, I'll just write down the final answer.
Sir, here you mistake divergence of del del. You write equation of gradient.
This is the gradient, na? Where is the divergence? I'm not writing the divergence.
In del. Sir, in del square term.
अच्छा, this is the, ये divergence लिख दिया है। नहीं तो divergence is that, this is not divergence. Anyways, let me just write down the expression. उसके बाद आप लोग मुझे चेक कर सकते हैं। 1 by r square दो r square दो r plus 1 by sin theta दो theta sin theta दो theta plus 1 by sin square theta दो phi square। तो ये है लाप्लासियन एंड स्फेरिकल कोऑर्डिनेट्स। ये गलत कर दिया मैंने, सॉरी। एंगुलर मोमेंटम इन स्फेरिकल कोऑर्डिनेट्स क्या होता है? हाँ, एंगुलर मोमेंटम इन स्फेरिकल कोऑर्डिनेट्स फॉर द सेम रीजन, व्हेन आई टेक दिस, मैं जब ये एल स्क्वायर टर्म लेता हूँ, आई कांट जस्ट take the dot product blindly. I have to be careful about it. So let me see. This is L. So let's see. If I take L square, that is L dot L minus H bar square, this dotted with the same thing. Okay, and now I have to be careful. This is the mistake I was making. I was not being careful. H square. So what are the expressions? See, I can't just take phi hat dot phi hat. The reason is because I get phi hat dou theta, then phi hat dou theta, like this. And here I was in a big rush to complete this. So I just assume that this is 0, right? Do theta, do phi hat, do theta, but this is not 0. Unlike the case for Cartesian coordinates, in Cartesian coordinates, you know that if you take this dou of x hat with respect to y, you get 0. And dou of y hat with respect to x, you get 0, right? And same thing for all the other terms. But in spherical coordinates, this is not true. And the reason it is not true is because if you look at this thing, this spherical coordinate system, what happens as you go around the sphere, this coordinate axis, these coordinate axes, they don't remain the same. They keep changing, right? So you can see that as you go around, r hat will change as a function of theta and phi. And same thing for all the others. So one cannot just, you know, blindly do this calculation. You have to be a little bit more careful than that. And then the other term you will get is theta by sine theta dou phi of theta by sine theta dou phi, right? You will also get in this expression, you will also get some cross terms like this, minus phi hat by sine theta dou phi acting on phi hat dou theta, and then you'll get another term which is minus phi hat dou theta acting on theta hat sine theta dou phi. But this will give you 0, and this term will cancel out. Okay, so you will be left with using this relationship, and then now you can use these relationships. There's that dou phi by dou theta, and actually this is 0. Okay, then okay, yeah, dou phi by dou phi minus r hat sine theta minus theta hat cosine theta. Anyways, this, so all of this you can work out in this is all in Zetli in appendix B. Okay. So the end result is the same, which is that the Laplacian operator can be written as I had written it correctly in my or almost correctly, 1 by r dou r square r minus 1 by r square h bar square L square. It's the final result for the Laplacian. Okay. So now when we ask, when we look at, for example, the eigenstates of the Laplacian, right? So we are asking what are eigenstates of the Laplacian. Those are eigenstates of this operator. All right, guys. So I'll stop here because I think you might have another class. Okay. Okay.
Yes, sir. Thank you, sir.
Yeah. We'll continue this on Monday, on Tuesday.